Kinetics, high level 3, activation energy and the Arrhenius equation. Essential idea: the activation energy of a reaction can be determined from the effective temperature on reaction rate. Nature of science. Theories can be supported or falsified and replaced by new theories. Changing the temperature of a reaction has a much greater effect on the rate of reaction than can be explained by its effect on collision rates. This resulted in the development of the Arrhenius equation, which proposes a quantitative model to explain the effect of temperature change on reaction rate. If you recall, an increase in temperature increases the rate of reaction due to two things. Firstly, an increase in the total number of collisions between reactants, and more importantly, an increase in the fraction of collisions that result in successful collisions. In other words, a greater number of molecules have enough kinetic energy to overcome the activation energy, as shown on the Maxwell-Boltzmann diagram below. At the lower temperature, you have far more particles with lower kinetic energy, and at higher temperatures you have more particles with more kinetic energy. And if this was the activation energy, you're going to have at lower temperatures you've got smaller areas showing a lower fraction of molecules with enough kinetic energy to collide successfully. It's the blue section. And here you would have at higher temperatures you've got a larger area. It shows a greater fraction of molecules with enough kinetic energy to collide successfully. So you're going to have higher frequency of successful collisions at a higher temperature. Also, the rate constant K is the rate expression for a chemical reaction, and it is temperature dependent. For any given reaction and any given concentration of reactants, the rate will only change if the rate constant K changes. And a general rule of thumb is that by increasing the temperature by 10 degrees Celsius, the rate constant will double. So at 15 degrees, the rate will be about 0.018. At 25 degrees, about 0.035. At 35 degrees, at about 0.070. So for every jump of 10, you get a doubling in rate constant. I'd like you to press pause and you can draw a quick graph of this. Just a rough graph draw there. Okay. The Arrhenius equation shows the relationship between temperature and the rate constant, K, more precisely. You can see we've got the rate constant here equals, it's the frequency or pre-exponential factor. So it's a constant for any given reaction, and it represents the frequency with which successful collisions occur based on geometry, collision geometry and energy requirements. Up here you've got the activation energy, you've got the gas constant 8.31, and you've got the absolute temperature in Kelvin. This is useful if you take natural logarithm of both sides, because then you can change it or manipulate it to make graphs, useful graphs. So let's have a look. If we arrange the equation slightly, we obtain this linear function. We've got the natural logarithm of K equals the activation energy over R for the slope, 1 over T as the x values, and we've got the intercept for the natural logarithm of A. So if we plot ln K against 1 over T, the slope is going to tell us the activation energy over R. So using experimental data for K and T, we can plot a straight line graph and use the slope of the line to find the activation energy, which is rather splendid. Another useful form of the Arrhenius equation is derived using simultaneous equations. You can see here, this form of the Arrhenius equation is useful when the values of rate constant K at two different temperatures are known with a high degree of certainty. You could simply stick in the two temperatures and plug in the two rate constants. You could rearrange it to calculate the activation energy. Oh, and that's that for a very short presentation. Splendid.